Well, thank you very much, Claude. And I think, as some of you know, I enjoy being the first or a pilot at many things. So I'm more than happy to do this. And because whenever you're first, you get to define, at least in part, what it is. And what I'd like to define this presentation to be is a celebration, maybe of my career, but I'd like to make it a celebration of my time at Purdue. I've had the pleasure of knowing, well, as I see you, I think I've met and known all of you, worked with all of you in some way or another. And I'd like to celebrate the times that we've had together. They've been marvelous. I love Purdue. I love what's happened here at Purdue. We've had a lot of fun. Some of you we've had maybe more fun than from time to time. So what I thought I'd do today is I'd mix a little bit of my research. I've learned a lot since I've been here. I think I still have a lot to learn. I think the best is yet to come, and I'd like to tell you about why I think that's the case. Okay, so since it's a celebration of a career, I do want to emphasize I really appreciate all that Purdue has done for me. The leadership has been tremendous throughout the years. I came in under Rex. I've had the pleasure to serve under Arvin, and nothing beats a great head, okay? I can imagine life would be a lot worse if I didn't have these tremendous heads. They have been so supportive of doing the unusual things I want to do. And I know that sometimes I'm sure they wonder where I'm coming from, but they're always supportive. So I appreciate that. And that goes for you too, Leah. I really appreciate the leadership. Okay, so I think if we're going to celebrate our time together, I'd just like to remind you the things that are most important to me, okay? Certainly Purdue is very important to me, but I would not be able to do anything without my family, okay? My wife, Christine, has always been my best supporter. She's been at some of my early talks in my life. I remember when I gave a not-so-good talk as a graduate student, she was there to buck me up. And then my children have been patient with me because I work some unusual hours. And so my family's been very supportive. My parents, when I graduated from Princeton, no one had graduated as an engineer. My brother was the first in our family to graduate from college. I was the second. My parents, that was I think one of the happiest days of their life. They just kept going on and on about it. Then when I graduated with a PhD in 1989 and told my dad the problem that I was working on, he says, "That doesn't sound that hard. Are you sure that you can get a PhD for doing that?" and I assured him, I said, "Yeah, Dad, it doesn't sound that hard." But amazingly enough, it's a tough problem. In my time at Purdue, I was an assistant professor from 1990 to 1994, associate professor, and I've been a full professor since 1998. The major positions I've been able to participate in at Purdue is I was a director of Discovery Park when it was founded. That was a lot of fun. I'll tell you a little bit more about that. That included being the founding director of the Reagan Street Center for Healthcare Engineering. And then one of my favorite jobs is I had the pleasure of being the interim head of industrial engineering. And that was a real eye-opener because of the interdisciplinary opportunities that opened up. And a lot of the ideas that came out of that are still active today. And that led to the engineering entrepreneurship and the West Coast Partnership Center work that I've done since I left IE. And really, it was launched by what I learned in IE and the contacts that I made in IE. Okay. So this isn't so much chapters, and I don't know how much of this I can get through. I mean, I've been working at this all day. I thought, well, I'll spend a few hours getting it together, just a few thoughts, and then keeping it orderly was a real challenge. So these aren't chapters. I would think of this like a bunch of musical instruments. You start playing one, then another one starts playing. I never really retire from a job. I take the best of the job with me, and that's been delightful. Every job gets more fun than the last because you have the elements of the previous job. My career was launched with a challenge problem. I learned about it when I was a senior at Princeton. Professor Littman from mechanical engineering challenged me on something called the traveling salesman problem. And I thought, yeah, that doesn't sound that hard. I'll work on that for a few days, and we'll see where we get on it. Anyway, that led to my Ernie Johnson at Princeton, and Professor Powell also reinforced that challenge and said it was representative of a wide range of problems. So I went to grad school wanting to work on that problem. I was very fortunate to have Egon Ballas as an advisor, who's one of the giants in integer programming, in operations research, math programming. And then I was a ChemE, and I had a great group of advisors at ChemE. Now, the reason I mentioned this PhD challenge problem is in my prelim, I made the statement to my committee that I was going to solve a 3,000-person traveling salesman problem. And they said, if you do that, you can graduate on the spot. Okay? Professor Ballas said that at the time, the record for traveling salesman problems, asymmetric, was 325 cities. So I was pretty brash in saying that I was going to do one that was almost 10 times larger. They didn't give me my PhD when I got that challenge problem solved either. But we did learn a lot from it. So it still drives my research today because this problem has a lot of properties of the problems that have great practical impact. So it's got n factorial answers. I'm not going to go through it, but this is the Euclidean version. You can draw it very easily. The question of my thesis was, can you solve large problems? Well, when I solved the 3,000 city problem, I solved many of them. It was a lot easier than we expected. So I thought, well, if they like 3,000, I'll see how large I can get. So we ended up solving, at the end of my thesis, and then into my early days at Purdue, I worked on it until my second or third year here at Purdue. We went up to Minneapolis and worked on a Cray supercomputer, which had a whopping 4 gigawords of memory. And I mean, my phone has more than that now, okay? Which is amazing. And we were able to do 500,000 cities. And really, that was just a nice round number. With what we had learned over a few years, we could solve any size you want. The only limitation was memory, okay? And that caused a lot of controversy. That's my most cited paper. And there's one branch of papers that cite it say, oh, it turned out it was a really easy problem. The other branch of papers said that there was some trick. And then some branch of papers says, well, that means we can at least do some of these problems, some instances of these problems. I explored over until about 1994, I explored many variations of the traveling salesperson problem. I looked at side constraints, Euclidean problems. What I learned is that the other ones were much harder with respect to the techniques we learned on the original problem, but I also gained enough confidence to believe that we could engineer any size of these variations that we needed to, okay? So that had a major impact on my career. After this work, I turned my attention to really a very practical class of problems, planning and scheduling problems. I wanted to go after problems that were very hard and that had enormous practical impact. Okay, so this early work, it was tempting to go down and work on these problems for a lot longer, but I thought we learned enough on this, enough theory, that we could attempt to do something in practical. Okay, one of the major things that came out, and this has been enduring in my entire career, is that NP-completeness is kind of a challenge to all of us, okay? So generally, there's a couple of philosophies about how to approach NP-completeness. One philosophy is that it's hard. You can only do approximate algorithms on it. Another class is, well, you should try these evolutionary programming approaches, or you try these approaches that have asymptotic properties. The approach I took, because it had the potential in my mind for maximum learning, was to treat them as engineering mathematics problems and postulate a class of them that you'd like to solve. And the way we postulated that class is we had something called a problem generator. So it's a polynomial algorithm whose output is an instance that you want to solve. Now, there's a lot to this, but bottom line is if you can write a computer program, a reasonably running computer program that puts out the instances that you want, then you engineer a solution algorithm for it, and it's because it's NP-complete, you're not guaranteed to solve them all. There's always some chance it might not work, but from an engineering point of view, you can solve a very, very large fraction of them. In the case of the asymmetric traveling salesman problems that are randomly generated, we never found one that we couldn't do, okay? Now, I'm sure under certain circumstances, very, very remote circumstances, you could generate an instance that would be very hard to solve, but it's just not likely. So the approach that we developed, and we've applied it to every one of these decision problems in engineering that we found, is we come up with a class of of instance generators, and then we start with a base algorithm and learn how to solve not only that one instance generator, but every instance generator of interest. And this can go on potentially forever. That's our practical consequence of NP-completeness. But since I have a very optimistic personality, my optimistic philosophy of this nasty class of decision problems is that we can engineer the sizes that we need to solve if we learn enough about them, okay? So that led me to another major concept of my research, which I'll get to. When I summarize all my academic work, this is my academic work. I call it classic academia. I did classic academia in the 1990s. I decided to be a little non-traditional in the 2000s. But let's review the classic. I still do classic academic work. I still have 4 PhD students. They happen to be in Chemi, IE, Aero, with Dan and others, and BME. I've got a BME student, and one of them is jointly advised with a professor from the College of Technology. So I still have a very active research group, but in the 90s, I was much more traditional. From the work, since I got here, I've got, if you count the papers that are in the mill right now, in the pipeline, I've got 90 plus publications. I've graduated 31 students, 24 PhDs, 7 masters. I've had 6 postdocs. My maximum group size was 13. I got that in 1996. My favorite thing to do is teach Chemi 450, especially with Professor Sorolla. And I'm very proud of the fact that we graduate out of that class about 4% of the chemies, okay, in the country. So I feel an enormous responsibility. I feel enormous reward in teaching that class. Some of the other things I've done, I was very blessed to have the POI award in 1990 because that really allowed me to have a lot of control over my early career. And I think it's given me, that latitude really has benefited my entire time at Purdue. For the 1990s, I maintained 200 to 300K per year for my research group. And in the 2000s, I've had multi-faculty awards because of Discovery Park and then all the things that Discovery Park has given me access to. In many respects, my academic career in the 2000s has allowed me to work with groups of faculty that would have been very hard to do without the introductions that Discovery Park had made. Not only has that had benefit for funding, but in terms of the kinds of problems like the missile defense problems, Dan was wherever Dan is, and the cancer care engineering problem with Marietta Harrison and many others, and then some of the things I do in some of the other things I do in defense, all was made possible by the contacts in Discovery Park. So it's really changed the equation. I don't ask how much funding we need. I usually ask what do we need to crack the problem, and the funding fortunately has been available because of these various connections. Okay. Now, the core of what I do, and the core of my classic academic work, is geared to attack complexity. Now, that complexity manifests itself in manufacturing. When I work alone, when I work to do something very hard, it's usually in the manufacturing area. And when I talk about complexity, there are lots of ways to look at complexity. But in manufacturing, you've got complexity due to combinatorics. Okay, you can change the sequence of a small number of items and get a huge number of solutions. You can have uncertainty and variability. If you're making a batch of, if you're doing a cell culture and you're making a batch of medicine from genetically engineered mammalian cells, it's inherently uncertain, it's inherently variable, and inherently that means there's risk in your manufacturing process. Okay? The interaction of details I hinted at with the traveling salesman problem. When you change the character of the problem, you change its difficulty. So in manufacturing, if you make what seems on the surface to be a small change, you can get a wildly different solution space, a wildly different answer. And so this is one of the places where complexity theory rears up and makes life very hard. Okay? And then in the 2000s, one of the things we've tried to do is tried to put humans in the loop. So that they make things a lot more complex in ways that we've had a great deal of difficulty in characterizing formally. Okay, so it's a quick tour through my classic academic period. I would say a main result, and I wrote a paper by myself in 2000 that was entitled Knowledge Acquisition Frameworks, and a little bit more description. But basically it was a paper about knowledge acquisition frameworks. And this is what I believe is one of our major intellectual tools to attack complexity. Okay? Now, what is a knowledge acquisition framework? Okay, so I'm fairly theoretical when I do my own work, fairly abstract. It's a framework is it can be a piece of paper, it can be a piece of software, it can be an algorithm that evolves, but it's a framework that allows you to observe phenomena, characterize this phenomena, and then the framework allows you then, when you learn something, to use the phenomena to accomplish some goal. Okay? Most of my knowledge acquisition frameworks are algorithms or software, or you put a GUI along with some software so a human can be part of it. But the main thing is, like the traveling salesman problem, if you get an instance, you make an observation as to whether your current algorithm can solve it or not. If your current algorithm cannot solve it, what that means is it takes too long for the amount of time you're willing to wait. You analyze it as to why it takes too long to solve. You figure out why it's taking that large number of steps, and you change your algorithm so it runs much faster. Okay? It's that simple. It's just that it's the kind of properties you have to observe that makes it a little bit more challenging. But basically, you make observations, say about the traveling salesman problem or a biological manufacturing process. If you get some behavior you don't like, you engineer based on the observations, then you enhance your framework to achieve the goal, and you move on. Okay? Now, over a long period of time, not just with my own research group, and now with the company, I'll tell you about that next after the classic academia, the practical result of this is that over a period of time, if you choose very powerful frameworks, you can mitigate complexity to a large degree, like going from 325 cities to 500,000 if you use that measure of complexity. And it allows you to be very goal-oriented about how you learn. If I'm very interested in biological manufacturing processes and I apply my math programming techniques and I keep re-engineering them until I can solve the problems I'm interested in, say a plant in Belgium or a plant in Great Britain, then you're applying your framework to something that you care about, and you work towards achieving your goal. Okay? I could give a longer talk on this, but the bottom line is, with NP-Completeness, you could study and go down an infinite number of holes of complexity. The purpose of these knowledge acquisition frameworks is to direct them towards things you care about most, and then just learn what you need to learn in order to achieve the goals that you want to achieve. Okay, if you're designing a specific plant, if you're trying to optimize a particular manufacturing scenario, or whatever. Okay? So this is one of the things I'm proud of, and the paper from 2000 was our first recognition that these frameworks existed. Okay? Now, so I thought I'd pull one of the more elegant, or one of the more self-contained examples of a knowledge acquisition framework. My IE friends will know of a problem called the B-matching problem. So if you have a graph, it's just some construct, and you're looking for a subgraph from that graph that has certain properties, namely that you have B edges in the subgraph from the original graph, and you'd like to choose the edges in such a way that they have certain properties like minimum cost or something like that. It's not important for this talk. For the celebration, it's enough to say that there's a mathematical formulation of it, okay? And if you say it in words, it's really not that difficult. But the bottom line is you can convert these equations to a set of properties which must be true of any solution, okay? The other thing you notice about this formulation, if you studied it for any length of time, is some of the constraint families have a large number of constraints, an exponential number of constraints. So you can't deal with it directly. You don't just throw it in a solver and get an answer. So what we did is we built a totally dedicated algorithm for this problem. And being an engineer, not a mathematician, and not even pretending to be a mathematician, our algorithm, we knew wasn't going to work. We simply said we'd run it on the computer and generate instances using one of these generators. We would keep generating instances until these conditions, which must always be true in any solution, didn't work. Then we would take that instance, analyze it, figure out why our algorithm broke, fix the algorithm, be able to solve all the other instances we solved before, and then that one. And then we ran it again. And kept doing that until let me get to the chase. We kept doing that for 18 months, and we ran millions and millions of instances. And after 15 learning events, our algorithm never ran into after we ran it for 6 months, 8 months, it didn't come up with an instance that was broke. So we thought, hey, maybe it's right. Then we proved it mathematically. Now that's a very inelegant way to do a proof. We got a 2-page proof that this very sophisticated, very complex algorithm was correct. Each of these figures represents a case that one of our instances taught us about, that we then figured out why the original algorithm broke with respect to that case, and then repaired the algorithm. Now, that sounds like slugging through, right? The original work was done by a mathematician by the name of Jack Edmonds. His proof was so complicated that it was never published. It was more than 160 pages, and it was in Bill Pulleyblank's office, locked in a filing cabinet. Bill pulled it out and said, yep, it's more than 160 pages. How many pages is your proof for your algorithm? We said 2. And the reason why is because the computer taught us how to think about the problem totally differently. Okay, so this is an example of a knowledge acquisition framework. And trust me, I couldn't prove anything else, right? But with the computer telling us every case that was of interest, we were able to come up with a much better way to do the proof and a much more intuitive way. And that paper was mildly interesting, but the other thing it taught us is, my God, if we have to do this for real problems, it could be 180 months or 180 years to do some of this stuff. So we figured we were going to have to make our knowledge acquisition frameworks much more powerful. Okay? All right. Now, this is one of my most theoretically capable students. His name is Paul Bunch. He was a Lilly employee over at Pekny Labs. He came to get his PhD after hours, then decided after he liked working on this problem, he came full time. Paul actually took all the results we did over this 18-month period and implemented them using just an off-the-shelf simplex solver with the exact same properties. So it didn't even have to have all the algorithm engineering that we originally had. He showed how you could do it with off-the-shelf software and get the exact same result, which was one of our niftier results from the classic period. Okay, latest work. This finishes up what I do in my research group and with my collaborators. But we've been working on agent-based models for energy systems. So we've done work with Indianapolis Power and Light on the effect of electric vehicles in Indianapolis. The first effect of electric vehicles in Indianapolis is going to have to be doing a lot of transformer investment. And we've had an interdisciplinary group of students from IE, civil engineering, chemical engineering, mechanical engineering, develop this energy system framework. And pieces of it have been published, but this is probably the most concentrated piece of that energy system model in INEC research. Okay, since this is not a talk just about my research, but it's a talk about all the things that I've enjoyed doing, what did I learn from my research group? Well, we learned that knowledge acquisition frameworks can be very powerful. We've been able to do highly customized linear programming and mixed integer linear programming solvers for problems from many companies. We've gotten test problems and challenge problems from all the companies that you've seen here. The Dow, we got a challenge problem from Dow that so many people tried working on that the plant manager made a video because he got tired of telling people about it. So he said, when we asked to work on that problem, they sent us the video in the mail and said, if you make any progress on it, then you can come and see us. One of my Indian students, Prashant Dave, actually was amused by that, so he watched the video day and night until he came up with an algorithm based on some of the stuff that we had done. And they used that, to the best of my knowledge, they still use the results of his PhD thesis to schedule that zeta, I can't tell you what the facility is. It's a metal sheeting, it's a metal sheet that they coat. So they still use that algorithm that Prashant Dave did at that Dow plant today. Anyway, the reason I have the companies in blue is that in 1993, we had done enough, some of the things some of the reasons we've been able to do highly customized LP and MILP solvers is that we've learned how to implicitly generate formulations. The analogy I give to my students is if you come in this room and there's a dungeon, no floor, when I take a step, the equations and variables are going to materialize under my feet and support me. I won't fall into the dungeon, and the equations and variables will always materialize under my feet, and where I've walked, they'll disappear. Okay, now that's combined row and column generation from my IE friends. I've used that trick in almost every problem that we've solved. So I almost never use off-the-shelf solvers. We almost always build these completely customized solvers that have this property, so they're never bound by the size of the formulation, because it's only the amount of the formulation that you have to support the solution, not the entire problem formulation. Anyway, we had enough results in 1993 when I was an assistant professor that several of these companies really argued for us forming a company. Now, 1993 was before it was fashionable to form companies. Okay? It was actually very risky to form companies. And somebody said, it's really impossible to form a company. Rex and a few other people had done companies. Pritzker was running at the time. He says, do you know what you're getting into? He Since somebody said it was very hard to do, I thought, I want to do it. Okay? So in 1993, as an assistant professor, I actually formed a company called Advanced Process Combinatorics. Now, fortunately, fate has been very kind to me, because one of the things it takes to have any chance of success in a company is great people, right? Always hang out with people that are smarter than you. Fortunately, the people that I started Advanced Process Combinatorics with, Don Miller from DuPont, one of the companies, one of the people who sponsored my academic research, left DuPont. DuPont actually provided money, seed funding for that company, and we formed APC in 1993, and it still exists today. Okay? Now, one of the things that APC has been able to do for me is I'm an advisor to it. I'm on the board. From time to time, I take leave and work at it. In the summers, I often work at it. APC has kept my research very real. Those folks have to get paid to do what they do. Those of you who work for Pritzker know the life. So these guys, the nature of the company, this is the sales media #1. They always talk about this knapsack problem, which is very easy to explain. This is their lead-in to get business. And the goal for the knapsack problem is to stuff objects in the knapsack so you don't go over the weight limit or the 80-unit limit, and put the maximum amount of money in the knapsack, not to go over the 80 units. These guys start off with this in the sales brochure, and this is their 64 solutions, and they illustrate there's constraints, objectives, you want a feasible solution, and you'd like to get the best possible answer. So this is the whole premise of Advanced Process Combinatorics. Unfortunately, they never get to solve problems that are this easy, but they have solved some problems which are, to my knowledge, the most impressive mixed integer linear programming problems that have ever been solved. They have applications which run on an everyday basis, from 10,000 binary variables, actually up to tens of millions of binary variables. This is an old slide. This is one of the slides I had on my disk drive that I could illustrate. But it still makes the point. This company works with solution spaces that are super astronomical. There's only 10 to the 80th protons in the universe. These guys are looking over solution spaces which are many, 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 many universes. Okay? And the fact that they can do it routinely is a credit to these knowledge acquisition frameworks, and the fact that these guys have been working. There's 114 person years of research in their technology, and it also shows that the limits of this knowledge acquisition framework idea are very far out indeed. The areas that they work on, where they can make money, well, they work wherever they can make money. And that's one, in that regard, they're like professors. They do a lot of work in process planning and scheduling. They do a lot of work in engineering analysis and retrofit, and some grassroots design. They've done some problems that were technical analysis of mergers and acquisitions, and some supply chain work. It's a combat R&D company, although they're starting to make the transition to a company that can scale. They've done some projects in research and pipeline management. They do a lot of work with Coca-Cola in warehouse and distribution center management, and they've actually won 5 SBIR or STTR awards, 2 of them through phase 2. So they've done some specialized applications like intensity modulated radiation therapy. I'm looking for my friend Hamid. Okay. What APC does, they've totally specialized their technology, completely customized it to solve problems that are formulated on a timeline, okay, that have knapsack-like constraints, that allow the user interfaces to control the structure of the solution. You can get the Gantt charts to appear the way you want, and that have precedence constraints in the material flow graph, or precedence constraints because of information reasons. Okay? And so they completely specialize in sophisticated management of constrained resources over time, and they're a viable business. They make money, mostly. Some years they do well, some years they do less well, but this is a going concern, and it's been of enormous benefit to my research. Not only do I know what I know as a Purdue professor, but since I'm a technical advisor, I never give up any confidences. I know what real challenges are up against. I could never know this information as a Purdue professor. The things that it does for my research, I couldn't know if I just worked here, if I didn't advise these guys, okay, and I didn't work with these guys. There's a real, I think, polarity, is that the word we're looking for? Tension between the two realms, but if you can connect the two realms, there's enormous learning opportunities. I think I learned that also from Steve Duckett from Pritzker, too, when I worked with him in IE. Okay, now what do these guys do that's unique? Because that's always the question. So the big thing that's happened out at APC is they've perfected for practical applications something called infinite dimensional programming. Very simple idea. You have a timeline. You have buckets for my IE friends. You take these buckets and you formulate over them. You don't lose any material in a bucket. Whatever comes in the bucket, whatever you make in the bucket, what goes out of the bucket because you used it up, whatever's left goes into the next bucket in time, just like the money in your wallet, Arvin. Okay? So if whatever Ramke doesn't take out in this time instant, it'll still be there. Okay? But I told you took it, right? You're head, right? You're still head. We take money from heads. Okay, anyway, this slide could have a lot of math on it, but the bottom line is each one of these lines of text represents a constraint family that APC can formulate. And what they do is these time buckets, when I was at Purdue, and we did this research in the 90s, these time buckets were 8 hours or 24 hours. What APC's done is they've shrunk the time buckets to infinitesimal slices and then use this dungeon argument where you step and only create the equations where you need it. Okay? And the number of equations is always some multiple of the number of boxes, say, on a Gantt chart. Okay? So this is really just the calculus idea applied to these formulations. And their solvers reason with these waveforms, which are these things that have infinite time resolution, and only the equations that hold up an answer ever get generated, the equations and variables. Okay? What's the result of this? Ironically, or I should say somewhat in a contradictory way, you can get good answers because it's math programming. You can rarely wait to prove optimality. You get very accurate answers because you don't have any, it tends to reduce the model mismatch. There's still model mismatch for other reasons, but not because of discretization. And here's the thing that was most surprising to me over the years, is even though you're solving these whopping big mathematical programs, because you only generate what you need, they're faster in most cases than heuristics. Okay? All right. Now, again, I am privy to this knowledge because I work on both sides of the fence, but it's very valuable even for some of the things we're thinking about doing for our current research projects, like with our current student in Aero. Okay, the history of APC, the early work was at DuPont in 1987. This is where my TSP work got started. They actually gave me a supercomputer to keep in our lab at Purdue, or not Purdue, at Carnegie Mellon, and that was on loan to us until we finished the TSP work and I graduated. So I was very fortunate to have that access to those resources. The pioneering work for all this infinite dimensional programming was a series of papers from the early 90s, and when we made enough progress, that's when the Industrial Consortium suggested we start APC. APC was spun off in 1993, produced version 1.0 in 1994, and I recall, being as optimistic as I am, by the end of 1994, I thought the company would be done. It would be sold and done with version 1.0. Okay? Well, they're on version 7.1. They're about to roll version 8, and they're now just getting to a version which can possibly scale. Okay? So it takes a long time to bring very advanced technology to practice. Okay? This is a lesson that was maybe in a major way unlearned in the dot-com boom. People started companies in the dot-com boom, and in a matter of 6 to 12 months, they would flip the company, even if it didn't have a business model that made money. Okay? What I learned from APC is you either choose your problems a lot more carefully and don't start a business on stuff that's simpler, but if you're going to start a business on something that's very, very complex, it can take a long time for that company to make it, okay, and scale. Okay? So APC's 17, 18 years in, and it's getting to the point where it can scale. Now, what are some evidence that it can scale? Procter & Gamble purchased a global license to their technology in 2000. I'm going to skip through this really quickly. There was a nice story about Hurricane Katrina that wiped out their massive facility in Louisiana. This technology was used to bring it back up on its feet within a matter of 3 days. It was the only plant that President Bush could visit because it was the only one that could be put back on its feet fast enough because of this modeling. So I thought that was kind of cool. When Bob McDonald, who is the CEO of P&G, was here in the last semester, he gave a little presentation about the impact of this technology on P&G, and most of what he said was in a confidential session, and that's in these two. But what I can tell you is they use it in more than 40 places, and they've saved oodles of money with it. How much money? If you look at all the research all the research funding I've ever had, it's 100 times that amount. No business office people go crank the number or I'd get in trouble, okay? But it's more than 100x the money saved on just one company using it. Now, I did kid Bob McDonald, so I would take additional money for my research if they're doing that well with it, and he chuckled. Always a professor. You're always writing a proposal. The last part of APC, and it also intersects with my academic career, in the last 6 years, I've been doing a lot of work with biologics. Biologics is mammalian cell culture. It's making very large molecules. You've got lots of large molecules in your body, so this is a very young business area. I've been doing a lot of work in optimizing the throughput in these facilities and designing these facilities and retrofitting these facilities. BMS, Bristol Myers Squibb, was kind enough to let us publish some of this work in 2007, and it really details developing a plant from scratch. And the reason why this technology is very important to doing that plant from scratch is because these plants are a symphony of activity. They have lots of support manufacturing that has to be done at just the right time to support the mainline manufacturing, which is the cell culture product and all the things it takes to separate it and get what's injected into the body. Okay, so these facilities are difficult to run. They cost a lot of money, $1 billion, and you often don't get the kind of throughput out of these facilities that you expect. Okay, so this has been a major target for me in the last couple of years. In fact, in 2012, I submitted an NIH grant, and people told me it was crazy to submit an NIH grant on manufacturing, but I put a grant in to NIH for improving the manufacturing of biologics, and I was very lucky they funded it. So if they say in a contrarian fashion never to do something because nobody else does it, that may be just the time to write the proposal. The purpose of this work is to understand and overcome the limitations in biologics manufacturing. I just submitted the final report for the grant. Okay, APC Learning, 19 years. They've got 1.2 million lines of code. It's hard to compete with a company that does research in an area that I used to do research in, so I abdicated that area. It generates a lot of jobs. Now, it's not that big a company, but there's a lot of Purdue PhD. There's 13 employees. 11 of them are PhDs. They're from Purdue, University of Texas, Harvard, Princeton. And it's a great lifestyle. I always call it a lifestyle company. The jobs are, it's heavily R&D. They're very high impact. They've got $12 million of R&D money put into their products, and they've got more than 50 installations worldwide. Academic company, one of the things I learned from this, and I think it's a lesson for what we're going to do here at Purdue in the next few years, academic companies start far too early, okay? We think that we publish papers, we think we've got research results, and it's ripe to be commercialized. We need to hold them in Purdue or hold them in an academic setting longer than we do now so that they can come out and have a lot better chance of succeeding, okay? APC is a very rare model. Most companies don't go on a growth curve for 19 years. There have been Silicon Valley venture capitalists that said, "Are you crazy?" Yeah, probably. But the point is, if you want to do something really cool and you want to do something really new and something really hard, it's not going to happen overnight. Okay? Now, the reason I say it's not unique is since I've done my latest job, courtesy of Leah, I've actually found a few companies that are just like APC, very long incubating companies that are working with very complex technology, and I understand it's a model for bringing some of this technology to practice. You can't get angel or VC money. It's too short term. Industrial partnerships are critical. If you solve their short-term problems, they'll be patient for a long time. Okay? Vertex technology has capabilities even billion-dollar-plus companies can't match, okay, because they don't usually hang in there that long. Academic industry partnerships, when done this way, can be spectacular, not in the short term, but over the long term, it can move quite a bit. Okay? But the people who work in these companies can't really just have a profit motive. They almost have to have a transformational mindset. Okay? So it's a little bit of a mix between academia and Adam Smith. Okay, I've got to watch the time here. I'm going to go quickly through the last couple of sound channels. What I do want to point out, though, Elliot may not be here, but Elliot Slamovich turned me on to another company just like APC. He did 2 sabbaticals with this gentleman. This is Steve Visco of Polyplus. He was a major researcher. He is a major researcher. He just retired from Lawrence Livermore National Labs. He worked for, of all people, at one time, Steve Chu. And Polyplus actually is an old company compared to APC. He started this company in 1987, and it's still developing product versions. And he's just getting ready to scale. So when I see him now, I always say that I'm the younger version of him, right? The fast-moving version of him, the .com version. Anyway, this company is attempting to make lithium-air batteries, which have the energy density on the order of gasoline, but you can recharge it. Okay, so it's rechargeable combustion. Okay, so it would be a game changer of the highest order if it worked. Okay, so one of the things I'm doing with one of my hats on is trying to engage PolyPlus, and that person who's my partner in doing that, I saw his wife, but I don't, Ernesto Marinero, there he is. So Ernesto is one of my latest partners, and he brings a lot to the table for this kind of work. Okay, I'm going to skip the Enterprise Center. Okay, I'm just going to give you guys the summary of the Enterprise Center because I want you to continue celebrating my talk and not keep you here too long. Okay, but I had the good fortune from 2001 to 2008 to be a founding director of this entity, Discovery Park, and I got to work with some really fun people who taught me a lot. My job was very simple, actually. My job was simply to help start up, along with Ned Howe, start up the Discovery Park processes, and then invest $8 million to catalyze large-scale research. Our number one investment was $1 million into NCN, and then our number two investment was almost $1 million into Sirius. So that represented about 25% of our investment. And then some of the other things you see here, Archie, Center for Catalyst Design and Chemie, LSN Squirt, and so on. And then one of the later ones was Cancer Care Engineering, which is still going on, and then the Institute for Defense Innovation, which is still going on. Anyway, Discovery Park started with $0, got $51 million over 2 tranches with the Lilly endowment, and today it's generated about $650 million in sponsored research funding. This is a major accomplishment for Purdue. What I've come to experience at Purdue is Purdue takes in stride major accomplishments. It's impressed with them, and then it internalizes them, and it moves on and utilizes them. But I find that what's been accomplished by hundreds and hundreds of people at Discovery Park to be maybe the basis for Purdue competing over the next several decades. The question is what's the proper relationship of it between Discovery Park and the academic units? It's a whole other talk. The last part of my career has been working on entrepreneurship, innovation, and commercialization, and Discovery Park has been kind of my base of operations for doing that. Discovery Park connects to the academic units with all the faculty, all the students, but it also has a large number of large projects. And one of the heuristics we've learned about Discovery Park is that for approximately every $1 million in research funding, there's a commercializable idea. Okay? So it has about $650 million in funding, at least 650 commercializable ideas. Many of them could be home runs. We just have to develop a system that cultivates the ones that are singles, from the doubles, from the ones that you get beamed, and the home runs. We're still working on it as a university. Just some things about Discovery Park, since I'm not going to talk about it in detail. It's put in almost $1.5 billion of proposals. If that was funded, I'd really be impressed. But it's gotten $305 million out of this is just a 3-year period. This is all I could get data for in the last couple of weeks. And the statistics over the entire 10-year time period are impressive. It adds up to the $650 million. Before Discovery Park, Purdue had, I think, a couple of proposals that were over $1 million. Leah has this statistic, but there were a small number of $1 million proposals. With Discovery Park, there are actually a $100 million proposal, that's the knees, 3 $10 million proposals, and then many $1 million proposals. I used to get an acorn for $1 million proposals, but then they quit giving acorns for the $1 million ones because I think they ran out of acorns. It wasn't because of me. They were giving them to everybody who were on $1 million grants. But that's how successful Discovery Park is. Okay, last thing, industrial engineering. I've only got maybe 5 minutes. Let's just say I'm particularly fond of industrial engineering. It's a great group of people, okay? These are some of my best colleagues on campus. I learned a lot about systems engineering, a lot about commercialization and entrepreneurship, working with my partner Steve Duquette. Ned Howe brought all the enterprise capability into from Discovery Park into industrial engineering, and then hand it over to Steve, who's taken it with Abby Deschmuke in great places. The only thing I'll say for industrial engineering, this was my first presentation for the Industrial Engineering Advisory Council. Because of my personality and I work on computers, I rarely get nervous or upset for that matter. This was one of the few talks I can remember giving in my life where I was a nervous wreck, okay? Because I was a chemie, right, talking to a bunch of industrial engineers, and I wasn't sure whether they would like chemies or not, okay? And this was in front of a group of alumni who, if you look at their accomplishments, every one of them is an incredibly distinguished person. Ed Schreck, Juan Ernesto Deboudet, Tom Weldon, the list goes on and on. What we did in industrial engineering, what I was privileged to do in industrial engineering really was watch the IEs work. What I did is I brought the resources from Discovery Park in, and I watched my IE friends like Shimon, Mark Leto. And the thing is, once you start naming people, you got to name everyone. I could literally name everyone on the IE faculty who ended up using these resources in some unique way I never would have dreamed of and doing something big with it. All I had to do was sit there, be reasonably nice, and connect the dots, which is my favorite activity in life. And I had Ned helping, and then ultimately Steve Duckett helping connect the dots. And it was a marvelous experience, so much so that when I got to my last presentation as IE head, I wasn't nervous anymore, okay? First of all, I was falling off back into burn up in the atmosphere, and Abby Deschmuke was taking over for me. And Abby's done a tremendous job. In fact, all I ever hear is good things out of IE because of the faculty there and staff and Abby's leadership. And I do want to call out one particular person. My partner in doing many things was Professor Richard Liu, and I really think very highly of him, and I'm very fond of him. Together we hired 4 assistant professors. We were able, with help from the Advisory Council, to find Abby. And 2 things that came out of this were the Entrepreneurial Task Force and the System of Systems Institute, which IE is still leading. And maybe the thing I'm most proud of, and this is because of the IE alumni, they raised over $1 million in scholarships for Professor Bernie, who I am extremely fond of. And we all miss him. Certainly the alumni miss him, but he was a great colleague. Okay, major learning. All elements of power of a school are awesome. If you look at what a school can bring to bear, the alumni, the research, the students, and the interaction between them, it is awe-inspiring what can be accomplished. In fact, I think one of our strategic plan elements, maybe the next strategic plan, is how do we challenge these schools to use all elements of power all at once and then even in concert with each other. Mobilizing alumni, we've mobilized them for an entrepreneurship task force and the Silicon Valley alumni, mostly from IE, to advise companies. And that group has really lit the campus on fire in a number of ways. It would be a whole other talk. The other thing about the other transformational elements is the right infrastructure is investment. Folks like Steve Duckett, when you add the right people, they make a huge difference. And then the other thing is leadership matters. Even informal alumni leadership in the form of folks like Ed Schreck do a lot for the school. Okay? The IE faculty are awesome. If you remove barriers from them, they do a lot. Okay. I think I better finish up. So instead of going through my last 2 slides, I'll just leave you with my conclusions here. What would I like to accomplish next in my career? Well, I think Purdue is on the edge of being able to do some historic things. When I look at the 2,200 faculty, and I've had breakfast with a good fraction of them, I've eaten over 1.3 million calories for Purdue, okay? I keep track of it. My family knows I keep track of it, okay? Now that's a lot of calories. If you think how many calories you get in a meal, that's a lot of meals, okay? So that's, the other thing I learned from those 1.3 million calories is faculty love to eat, okay? And if you eat with faculty, no matter how contentious the issue, you can get the business done, okay? So if it's really hard and we're eating, let's put it this way, if we're eating together, it could be a tough topic, okay? But from all these breakfasts and lunches and dinners, what I've learned is from all the good work of our 2,200 faculty, we are on the edge of doing something historically transformational, okay? But we're going to have to change our organizational structure to do those bigger things. And we do big things all the time. We've had astronauts. We've had the first guy on the moon. We do big things all the time. But the sense I get from my career is that even more is possible, okay? Because the technology that we're sitting on is so wondrous. I mean, this has got more computer power than my science article computer. And it costs, you know, I don't know, 5-6 orders of magnitudes less. Okay? That was one of the most expensive computers in the world that I used, and now more powerful hangs off my belt. I believe as bright as we are, we're in some sense imprisoned by the life we've lived, and we think technology is moving at a certain rate. I think it's moving far faster than the rate we're used to, and that if we think bigger and think how to organize ourselves a little differently, we could realize these transformational impacts. Okay? I think we also have a chance at Purdue, because of how well we're led and how well we've stewarded our resources, and the fact that we're growing in engineering, the fact that engineering is a big part of the university and it collaborates so well with the other parts of the university, we have a chance to define engineering in the 21st century. Now, the only thing I'll say, I told you I would stop, but what I want to say is, what I think it's going to take to define engineering in the 21st century, if you look at the Webster Dictionary definition of engineering, I've got it written here, but I've added one word, okay? The one word I've added in the 21st century is I think we should attempt to do rapid applications of science and technology and very deliberate applications of science and technology to go after specific goals, okay? And if you want a most recent example of deliberate innovation and rapid innovation, look up Iron Dome. If you want to, Israel has implemented something called Iron Dome. They did it in 3 years. And what it does is knocks down 90% of the rockets that are shot at it. And it does it very inexpensively. And it did it with off-the-shelf technology, admittedly from Missile Defense Agency. But in 3 years, they were able to create something that people thought was impossible. I think that can be repeated over and over again, and I think we should be the ones to do it. Okay, that's good. This is some of our stuff, Ernesto. I thought I'd throw it in there, but we'll leave that for another celebration sometime. All right, that's it. Thank you very much. Oh, I would stay all night. What do you think? Want to get to the reception? Any questions? John?
You ended with this conclusion about rapid development, but it kind of contrasted an earlier idea of your long-term company development.
It does.
So what are your ideas on the...
That's a good question.
In terms of saying starting companies too early is not a good idea.
It's
hard problems to
yes.
be a long time.
We have to incubate these long-term movements of very advanced technology, and then we've got to be constantly looking to apply them, because they can change like a phase change. They can go from one phase where not much magic is happening, and then because of just what appears to be a small change, you can combine them very quickly and make a big difference, like Iron Dome. Okay? Iron Dome would have been impossible to do 5 years ago or 10 years ago, but in the last 3 years, it became possible. Okay? So at one time, we as a university have to invest in very long time scale, very risky, very deep technologies, and we constantly have to strive to do it, even when we have to do a lot of applications. But at the same time, we've got to also have a sense of urgency. Okay? So it's a contrast between incredible patience and always balanced with an incredible urgency. Okay? You've got to have both. If you're too urgent, then you don't get the kinds of stuff like the infinite dimensional brain. If you're too patient, then you can work on that stuff forever. So we've really got to have both tensions. Okay, that's a good observation, Jim.
Joe, you and I had some discussions a few months ago about frustrations in dealing with companies in applied research and IP.
Yes.
So there are different models here going. So spinning out a new company with IP from Purdue versus working with existing large companies in a constructive way.
Yes.
What's your thoughts about what the model should be for Purdue, and are we getting there? Because I think we're starting from a low base, but there's things happening at the moment. So I'm interested in your thoughts there about applied research institutes and the like.
Well, I mean, there are reasons why a large institution behaves the way it does, right? It's not, I mean, we've got brilliant people in the university, and yet it seems to behave in some circumstances, maybe in ways that are counterproductive to doing something entrepreneurial. But there are reasons for that, right? The bottom line is we as a university have got to figure out innovative ways to be ethical, moral, right, legal. But other than that, we should be able to do anything possible to make something work, okay? I think with the leadership we have right now, the high-level leadership, President Daniels, Dan Hassler, I think what the kind of vibrations I'm hearing are that we're going to be legal, ethical, moral, but other than that, we're going to do whatever it takes to cut a deal to be successful. I mean, that sounds trivial, but the real brilliance is in every deal you do, you figure out how to get the deal done without getting ensnared, okay? That's the best I can do. It starts at the top, and then every level has to try to expedite and get around bureaucracy. It's a bad answer. It's the best I can do. Oh, Leah, sorry.
So, hypothesize that you are going to be the catalyst or a principal component of the catalyst or the Qualcomm scale.
Oh, you caught that. I didn't even say that one. You caught that one.
There's going to be a long list on both of these, but I'm going to just ask for one and, somewhere in the top few. What's the biggest barrier? And what would be the biggest enabler for you to be the catalyst for Qualcomm scale achievement?
Okay, so Purdue has 400,000 alums. Really, it has an alumni base that has, I think, virtually every skill we need or every resource we need to achieve that goal. We have 2,200 faculty, the most brilliant people I know, okay? Every one of them could give a talk like this that is a celebration of a long career of hard work and a lot of insight on a lot of the part of their students. Okay, the key to doing it is connecting the resources we need here. In other words, no historic transformation that would lead to a Qualcomm level company is going to be a small number of mental models. It's going to take hundreds of mental models put together in just the right way to productize something big, okay? That means we're going to have to be able to connect the right faculty, and then we as faculty do not have the resources necessary to iteratively refine. We need lots of money, but you also need to understand the markets in a very deep way, because a subtle change can make it successful or unsuccessful. So we have to be able to connect with our alumni base, the right faculty. If we do that in the right combination, I think we can get a Qualcomm level success in the next 10 years. Maybe, and you would have milestones to get there. You'd have more companies being formed, that you'd see lots of good pilots, lots of good prototypes. So you don't have to wait 10 years. You would see a lot of it. I think you're starting to see some of it now, but I don't think we have enough connectivity in our network. I think our network still has limited connectivity. Okay? It takes a lot more calories than 1.3 million if we're going to have a Qualcomm level company. I mean, the Silicon Valley guys, just because of the numbers, they have 6 million people. We have 6 million people in Indiana and 100 times the land mass, right? So they can eat calories with a lot more density than we can, all right? And really, that connectivity and smart connectivity is what we're missing, in my opinion. Okay, we can flog ourselves and say we're not as entrepreneurial, and there's some cultural elements that are true. We can get better culturally, but some of it is fundamental. If I put you in an environment that has 1/100th the atmosphere, you'll behave differently. Okay? So we've got to put a spacesuit on and make those connections deliberately. Does that help? Okay. Ernesto.
What would you change? What would you improve to make our students more participant in that rapid transformation of the education?
I think we need to give them more opportunities to participate. We give them lots of opportunities to participate in research. I'm pointing at Chip because I know in civil they do a good job. I've seen Chip do a lot of undergraduate research. He's sitting right behind you. I noticed he was there. Thanks. We have them participate in research. We need to get more of them participating in these kinds of endeavors, and they need to see what success looks like, okay, or the beginnings of success look like. We have a program that Lilly Endowment has endowed. It's called IDI. No, it's called Interns for Indiana. I forget the exact, IFI. Now that program has shown some success. I just think we need to figure out ways to get more and more of them involved in startup activities of all kinds. I think just like we make great efforts to get them involved in research, it's going to take great efforts to get them involved with this sort of stuff. Arvind?
Sure. You identify, say, during your career, some things that you may have done differently with the hindsight that you have now that could have had even greater impact in various of it. You had enormous impact already, I know. This is recognized. But
I think just like that, Arvind.
yeah.
I always think if I get, one of my favorite movies is Groundhog Day, right? So I often wonder if I woke up, now my wife's probably thinking this is a nightmare, but if we woke up in 1990 again, what would I do differently for this next pass?
Yeah, so now it's hindsight. So what steps could you have taken at some points which what you did do led you to what you are here, but could have been very different?
This is an easy question, actually. This is an easy question. I would have started APC a lot later. Instead of starting it in 1993, I would have started it in 2000, okay? It started way too early, way too early. It was like a child born at 5 or 6 months, okay? And it just wasn't ready in so many regards. And when I took sabbatical, most of the time was just spent doing basic things that really didn't add near as much value. In hindsight, I can see what needs to be added to be successful. And most of the companies that we start are started way too early. We should have some kind of incubation program that goes from research to prototyping and piloting, first customer program inside the university, right? Almost to it's embarrassingly ready to go outside. It's like having a 23-year-old living at home. My daughter is living at home with us, right? Where you think, well, they could be out on their, no, we, yeah, right. Just got that little dig in there, honey. But we need to keep our companies and our ideas taken to practice internal much longer. And that flies in the face of academia, or at least classic academia. I think academia of the future, that'll have to be the default. Okay? Now that's the number one. Right? That's the number one Groundhog Day observation. Now there are many smaller Groundhog Day observations, but you'd have to get, I mean, I'm not sure some of them are structural. I would have liked to have bought Google stock in 1999. Then I would be endowing the building for you, or endowing some other building for somebody.
You have to name the school.
Right, right. Any other? Girish.
If you think portfolio management is difficult, how complex will the management of 2,200 professors with, let's say, 3 ideas each and 400,000 alumni, how will you select the projects or candidates to support?
That's a really good question, Girish. First of all, I would say we're already doing it a certain way, right? Because we do have the 400,000 alumni and we do have the 2,200 faculty. So I would call that the null approach, right? We're doing something already. The question is can we do something better than what we're doing now? Okay? And the answer is, one, I like analogies, I like stories, I like military history. I would say this, we only have to be partially sighted in the land of the blind. We only have to do better than all the competition and help show the way to how to do it, and others will copy us and show us things. So, we need to find a group of alumni, I think hundreds of them. We have something called boiler innovation groups in Silicon Valley. We should get them in Austin, Boston, Chicago, maybe a few other places where there's lots of boiler makers. And those groups can be the initial set of alumni. Choose them so that they have a lot of research experience or a lot of innovation experience. And there's your set of alumni, I think. IE has an incredible number of entrepreneurs, and that's where the ETF came from, the Entrepreneurial Task Force. Okay, then faculty end, that's harder because I'm a faculty member. You can't tell faculty what to do, and I don't think we should. So you gotta create programs that are voluntary that the faculty can participate in. And what I learned in Discovery Park, only expect 10% of them participate. Leave the other 90% alone doing what they're doing because they're the ones that make the university. They're the ones that are doing the things so that we can have a university that can do all these great things. So I think we should have faculty fellows who enjoy doing this, and their job should be to try to de-risk technologies, to help push prototypes along, and get the things ready inside for connecting them to our alumni. Okay? So we have an internal system. It has to be led by faculty. Has to be faculty. Because if you don't have a faculty member talking to another faculty member saying, oh, that's going to take a long time to do that, it's hard enough for a faculty member to do it. So I think we should have something called Deliberate Innovation Faculty Fellows. I think that's a good term. So that we can have boiler innovation groups and deliberate innovation faculty fellows, and we can make a big diff. How's that for a question and answer? All right. Any other questions?
One last question. You've said that we're all smart.
And that's true.
We're all working hard.
And you are.
So something must still be lacking in the fact that there isn't that rapid application. So what enabled rapid application, I guess, is somehow function differently.
Okay.
What's the essential change that you suggest?
Well, Ramke, that is a question I've been thinking about for the last year now. And let me use a historical period to answer your question. Let's consider World War II, because everyone knows I like military history. World War II, from 1941 when the U.S. entered the war till 1945, there were hundreds of technologies brought from the labs to practice. Materials for armor, radar. Radar created Silicon Valley ultimately. Manhattan Project, the nuclear bomb, right? And if you go down the list, it's unbelievable, really, okay? And I have gone down the list. Now, that was the most prolific period in human history for translating research to practice. What did they have? They didn't have Google. They didn't have a smartphone. Their smartphone was something like you put a shoe to your head or something, right? So they didn't have any of the technology we have. How did they do it? How did they bring all that research to practice that quickly? Well, they had a sense of urgency about them. They had a sense that their lives depended on it, and that if they didn't do it, they were going to die. Okay? Now, I think with all the technology we have, I'm not advocating that as a management. Arvin, any department heads in the room, I'm not advocating any management techniques here, right? Right. No, what I'm saying is yes. Well, under certain circumstances. What I recommend is that we supplant technology for that life or death feeling, and I believe we could create a system that was as successful or nearly as successful as what they did in World War II. I think it's possible, okay? Just like Vannevar Bush created a system in peacetime to have the current academic system we have now. That was created as a cold shot to overcome Sputnik and all the science problems that they perceived in the 50s, right, 40s and 50s. So they created a system which we all benefit from today. It's time to add something to that system to recreate the conditions that we had in World War II, or the Apollo. If you don't like World War II, fine. You want a peace example, the Apollo missions, great peacetime example. Okay, we need to recreate that. But I don't think we need to recreate it on a grand scale. I don't think we need to go to Mars necessarily to get the benefit. I think each of us individually or as small groups have to come up with our own version of the Apollo project. I think you're doing that with personalized medicine. What I saw yesterday in the cancer care engineering presentation, I think that's a big advance. Okay, and that's an advance that is kind of a deliberate shot, right? And it's taking 30 years of your research, which is fantastic work, and you're deliberately using it to get a very practical clinical result, yet one that you couldn't get without all the research that you had done, right? Okay. Yes, sir.
I feel like you have consumed 1.3 million calories in the last hour. So that was a real energizing talk. Let's thank Joe one more time.